Let us now take a look at radicals. Let us recall if you have nth root of x, the thing inside your radical sign is called your radicand. This is your radical sign, and that small number over here is your index. Let us recall the following. If you have a number raised to a fraction, like this one, a number raised to a fraction. So what you do in terms of radicals, that means that the denominator becomes your index and your numerator becomes an exponent. Alright? And then if you have the nth root of the nth root of a, you simply multiply the indices. And then, of course, the nth root of a raised to n is equal to a. Why is that? Take note that in terms of rational exponents, this means that we have a raised to n over n, which is the same as a. So how do we simplify radicals? So for our first rule, if the index is odd, there should be no negative sign in the radical. So for instance, we have cube root of negative 8. What is cube root of negative 8? We're thinking of a number such that when you cube it, it's equal to negative 8. So the answer is negative 2, right? Take note that cube root of negative 8, we can write that as negative cube root of 8. So how do we fix if we have a negative sign inside the radicand? If the index is odd, you only pull out the negative sign. Warning, you can only do this if the index is odd. You cannot do this if the index is even. Meaning to say, I have square root of negative 4. That's not the same as pulling up the negative and then 4 because the right hand side is equal to negative 2, whereas square root of negative 4 is an imaginary number. Okay? For our next rule, a radical is in its simplest form if the exponents of their factors in the radicand is strictly less than the index. So if it's not the case, how do we fix it? We divide the exponents of the factors by the index. Let me illustrate that in this next example. So for instance, we have cube root of 32 times b raised to 20. Remember that if you have radicals, whenever you see your coefficients, the coefficients should always be in its prime factorization. So the prime factorization of 32 is 2 raised to 5th, b raised to 20. And then we can split that using the laws of radicals. 2 to the 5th times cube root of b raised to 20. Now, let us convert this into rational exponent. So for this first one, this means we have the base 2. The numerator is 5. The denominator is your index. And then, this one is b raised to 20 over 3. Now, what is 5 raised to 3? In mixed form, that is 1 and 2/3, right? This is 20 over 3 is 6 and 2/3. What does it mean to have 1 and 2/3? Take note that this means 1 plus 2/3, 1 plus 2/3. So what I will do next is split this 2 raised to 1 plus 2/3. Let us recall that if we have a raised to m plus n, that is equal to a raised to m times a raised to n. right? So, going back to this one, we have 2 raised to 1 times 2 raised to 2/3. And then similarly for your B, we have B raised to 6 times B raised to 2/3. So let's collect everything without the rational exponents. So we have 2b6 and then times 2 raised to 2/3 b raised to 2/3. If we turn this into radicals, this is cube root of 2 squared, cube root of b squared, and then you have 2b6. Okay, so meaning this is equal to 2b6. I'll put them together inside one radical sign. So 2 squared b squared or 4b squared. That's a bit long, right? Now what will be a shortcut for this one? So in here, what's important is that the main thing here is this part where 5 over 3 is equal to 1 plus 2/3 and 20 over 3 is equal to 6 plus 2/3. Now, if we want to do it the shorter way, from cube root of 2 to the 5th b raised to 20, what you just need to do is divide the exponents with the index. Let me just show this one. We just have to divide the exponents with your index. Alright, so similarly also with this. So 5 divided by 3 is 1. Let me just get my pen. 5 divided by 3 is 1. So the exponent, so we have 2 raised to 1. 5 divided by 3 is 1. Remainder 2, right? So the remainder 2 stays inside. That with the same base 2 pa rin. And then for B, 20 divided by 3 is 6. So we have B raised to 6. And then remainder 2. So what happens there is, so we have 2b6 cube root of 4b squared, which is exactly what we obtained here. Okay? So again, let me just write down what happened there. So whenever you have b raised to m and then nth root, wherein your exponent is bigger than your index, so all you have to do is divide. So you will get b raised to quotient and then index, and then the remainder remains inside your radical sign. Okay, next. The greatest common factor of the index and the exponents of the factors of the radicand must be 1. Let me just illustrate that. For instance, we have this fourth root of b squared. Now, this is not yet in simplest form because the GCF of 4 and 2 is not 1, right? So how do we fix it? We divide the index and their exponents by their GCF. Meaning to say, since the GCF of 4 and 2 is 2, we divide both of them by 2. So 4 divided by 2, we get 2. So since the index is 2, we no longer write that. Then b 2 divided by 2 is 1. So that's why it's just square root of b. What is the reason behind it? Take note that if you look at your 4b squared in rational exponents, this is the same as b raised to 2 over 4. And 2 over 4, right? That's the reason where the GCF comes from. 2/4 is the same as 1/2. Clear? Next. Lastly, there should be no radicals in the denominator. How do we fix it? We rationalize. How do we rationalize? So it depends how your denominator looks like. If the denominator is of this form, we multiply both numerator and denominator by this expression over here. What does this mean? This is actually saying that what we want to achieve here is, so take a look at this one. If you multiply it by nth root of a raised to m minus n. Oops, sorry. It should be n minus m. Let me just erase that. A raised to n minus m, we get nth root of a to the n, which is really equal to a. So there, the radical sign is eliminated. Next, if the denominator is of this form, if meaning to say you have a binomial and then with square root, or you multiply both numerator and denominator by square root of a minus b, so that you will end up with difference of two squares. For example, 2 over cube root of x squared. Now, what will we need for the denominator? We multiply it by, so here we have x squared. We want to end up with cube root of x cubed. We want to have the same number in your index and in your exponent so that it will just be equal to x. So therefore, what do you need? For x squared to be x cubed, we just need x. Correct? So cube root of x. So therefore, we have 2 cube root of x. Oops. 2 cube root of x. Then the denominator is already x. So 2 cube root of x. Clear? Let's now look at an example wherein the denominator is a binomial with square root signs appearing. So for instance, we have 1 over 2 plus square root of a. So in this case, we rationalize it by multiplying both numerator and denominator by 2 minus square root of a, 2 minus square root of a. Why do we need to multiply both numerator and denominator by the same expression? Take note that this is just equal to 1. This thing over here, this is just equal to 1. So meaning to say, we're not changing the original expression. Moreover, how come we need something, how come we need minus here and plus here? So that we have difference of two squares or dots, right? So we now have, let's continue with our solution. So we have 2 minus square root of a all over. So this is dots. So square the first term minus square the second term. So we now have 2 minus square root of a all over 4 minus a. So that's it. That's the rationalized version. I have here a summary of the rules of simplified radicals. So whenever you're simplifying, again, you have to make sure that you do this in order. So meaning to say, you should really check this one. If the index is odd, there is no negative sign. The order is important here whenever you're simplifying radicals. Okay, it's better if you follow this when you have to do that simplification of radicals. Alright, so for addition and subtraction of radicals, take note that you can only add or subtract similar radicals. Similar radicals are those that have the same index and radicand. Now, sometimes you will be given terms wherein if you take a look at it, at first, it seems as if they are not similar. So what you need to do is to simplify the radicals first so that you will be able to see all the similar radicals. Now, well, this is a very easy example. There's no way we can simplify the the terms over here. They're already in simplified form. So we can just add those that are similar. So I have here, let me just put them everything. So we have 3 cube root of 4 minus cube root of 4. The similar radicals, I will put them together. Plus square root of 2 minus 4 square root of 2. So we now have, so we just treat them as if they are polynomials, wherein this is like x, right? So we have 3 minus 1, the invisible one, so we have 2 cube root of 4, and then square root of 2 minus 4 square root of 2 is minus 3 square root of 2, right? Operations on radicals. So let us recall, if we're adding or subtracting, we need to have the same index and same radicand. However, for multiplication and division, we only need same index only. Why is that? Because for radicals, we have nth root of a times nth root of b is equal to nth root of ab. So meaning to say, as long as you have the same index here, all you have to do is to just multiply the radicands, all right? So these are the rules that I was talking about, and also for division. So as you can see here, if you have a fraction inside your radical sign, you can also distribute the radical sign in the numerator and in the denominator. Alright, so for instance, we have cube root of 2x squared and cube root of 2xy. So we already have the same index. So meaning to say, we can just multiply the radicands. So we now have, let's copy the index 3. Cube root of 2 times 2 is 4. And then x cubed y. And then we can still look at this one, x cubed. So we can still pull it out. So we can pull out the x. Oh, it will look like an exponent. Let me just erase the 3 there. All right. So we have x cube root of 4y. And for this one, square root of 125 over 5, take note that you can simplify, the radicand first. So in this case, we now have 125 over 5 is equal to 125 over 5 is 25. So square root of 25 is 5. Alright, so for the next example, we want to find an equivalent expression for 7 this expression over here. All right, so let's attack. So what will we do? Rationalize, right? We need square root of 7 plus square root of 2. Oops, not equals, but multiplication. Square root of 7 plus square root of 2. So our denominator will become the square of square root of 7, which is 7. We have difference of 2 squares, minus 2. And then for the numerator, we have, they are just the same. So square root of 7 plus square root of 2 squared. And then let's now expand. How do you square a binomial? Square the first term twice the product. So we get square root of 14 plus square the last term, which is 2 over 5. So let's simplify the numerator a little bit more. We now end up with 9 plus 2 square root of 14 over 5. Let's look at this one. The quotient of this expression in simplest form. Alright, so let me first write this in fraction form. We have square root of 24x cubed over square root of 27y. Since they both have square root sign with same index, right? 2, we can put them in a single radical. 24x cubed over 27y. Why am I doing this? Because I already saw that I can turn this into lowest terms. We now have 8x cubed over 9y. Recall also that we're not allowed to have fractions inside your radical sign. So that's why we need to separate them. Square root of 8x cubed over square root of 9y, we get 3 square root of y. I can still simplify the numerator. Let us recall that if you have a coefficient inside your radical sign, in this case 8, and it's not a prime number, you should always express it in its prime factorization so that you can simplify the radical. Let's do just that. 8 is 2 cubed, and then x cubed over 3 square root of y. And then the numerator becomes 2x square root of 2x. So remember, right? What do we do with the exponents? If the exponent is bigger than the index, you divide the exponent with the index. So 3 divided by 2, you get 1 here. Remainder 1. I forgot to write my... Ah, that's right. We just finish 3 square root of y. And then we still have to rationalize it by multiplying it by square root of y. How come I'm only multiplying it by square root of y? How come I'm no longer writing the 3? You no longer need the 3 because you just need to remove the radical sign. So you just need square root of y. You don't have to include the coefficient. We now have 2x square root of 2xy all over 3y. That's it. Let's now proceed with solving radical equations. For radical equations, our goal is to eliminate the radical sign. But first, how will we do that? We have to isolate one radical at a time on one side of the equation. And then, remove the radical sign by raising both sides of the equation to a given exponent. So warning, if you have rational equations, don't forget to check for extraneous roots. Let me just remind you, when do you need to check for extraneous roots? only for rational equations and radical signs. Although, for rational equations, you don't really have to substitute pa. All you need to do lang there is to make sure that the answer that you obtained will not make the denominator 0. Let's look at this example. We have square root of x squared plus 7 minus 2 equals x plus 1. Let us isolate this term over here. Square root of x squared plus 7 equals, we have x plus 1 plus 2, 3. Then we want to eliminate the square root sign. So we raise both sides to 2. We end up with x squared plus 7 equals the square root of x plus 3 is x squared plus 6x plus 9. We can now cancel x squared, x squared. So therefore, this is just a linear equation. Isolate x, 6x equals 7 minus 9, negative 2. Divide both sides by 6. So we get that x is negative 1/3.